Coffee stains and name chains. I am such a loner. San Francisco bases got me slowly taking over. I can't wait to show you that I'm gonna take it over. Lico, beast mode, 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 Lico, beast mode. This is not a main thing, really I'm a coder. Coffee stains and name chains, I am such a loner. San Francisco bases got me slowly taking over. I can't wait to show you that I'm gonna take it over. Lico, beast mode, 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 Lico, beast mode.
Let's get it. Final day, Advent of Code. Finale. Who's ready? I would literally just been studying day 10, things about linear programming and stuff like that. Oh, my back hurts. I've been working all day. Sitting down all day. I've been sitting way too long because I've been working and then also doing this challenge. So I'm just spending so much time just sitting down. After this, I'm going to go for a lot of walks after this Advent of Code. Give some time for everyone to roll in. Fix my camera real quick. How's everyone doing today? Damn, my back hurts. Send this over to Discord. I'm working through day 10. We still have 45 minutes, so we're just going to chill out for a sec and try to solve day 10 before we get to day... Yo, Ramen. I finally understand day 11. Or, sorry, day 10 part 2. Lico, beast mode. Nobel, what's up, man? I'm going to see you in like 7 days. Happy birthday. We got to celebrate at some point. You and Jules. We'll do something lit. How's Calgary been? Yeah, I'll be back for sure. Bro, I don't miss Christmas. Ever. Yeah, I'll be back on the 18th. What have you been up to, Nobel? Ramen. I just use ILP solver. What's ILP? Integer linear programming? Oh, yo, we can do it at the new house. Nobel, I haven't even taken you to the new house yet. We'll take you to the new house and we could play there. It's gonna be crazy. Gotta put some money on it this time. Yes, sir. Anyone stuck on 11 part 2? Nah, we solved part 2 of day 11. Do you have questions on it? Yeah, I'll put some real money on it. And then we'll hit the casino again for some revenge, because last time it did you dirty, so we gotta go back. Ego, what are you saying? Like, you want to see my code? I'll send you my code for that. It's kind of simple. It's like very. It's just like a DFS with backtracking, or sorry, it's a backtracking algorithm with it's like a DP backtracking. So essentially, this is my code. I built the adjacency list, right? The adjacency list is what maps is like where pretty much is a default dict of like each node to its neighbors, right? By parsing this out. Then I just perform a DFS or like a backtrack. I should probably label it backtrack, starting from SVR. And then we keep it. This is the base case. Like, or sorry, not the base case, like the closing case, like when it should stop. Yeah, that's the base case, I guess. Yeah, this is the base case. This is where we do the cache, and this is like the recursive case. So we pretty much just try every single path, and we're minimizing the result. Or we're not minimizing, we're just counting. Yeah, if we seen it, we just return true. So we're basically memoizing we're basically memoizing on 3 keys. The node, like this is our cache. The node, if we seen DAC or seen FFT. Oh yeah. That would be a funny Christmas stream. Yo, Alpha, I'm gonna do some prep and then I'm gonna sign up for one of your coding interviews. You gotta give me like a normal one though, like just straight up like what you would give at a regular company. I used to give you normal ones, but I gave you like 10 interviews at this point, so it just gets slightly harder each time. To the point I gave you like 4 hards in the span of 45 minutes, but that video did well, so. Yo, were you able to solve part or day 10 part 2? That's what you say? Fang Senior gets fried. Yeah. I'll just totally flop it. Like, then just start coding without saying a solution. Yo, Alpha, your videos are doing pretty good though. I was watching them. I hyped one of them, gave it like 1,800 hype points. What is it? Let me find this guy. Yeah, honestly, I never knew why people like the interviews because they're usually long. I guess you want to see if people are gonna flop it or not. Yo, I was looking up like reduced row echelon form. Yo, Alpha, just you should add like little timestamp on yours real quick too. When you go like, just like build out a like a little AI to do that. Do this. The way I just build the timestamp is I go like this. I just grab the transcript. Shoot. Then like on my website, you can build this out if you have your own website. I have like generate timestamps. I just quickly go like this. Should take a few seconds. Just so people, and like it throws some. Yeah, just you should build out your personal website and just like be able to like add as much features as you want to it. And then like all you have to do is drop it like that, and then it should add chapters, cause it's long, right? So we can know when, like, the different parts of the thing real quick. Yeah, that'd be sick. Maybe we should do like a challenge like that or something. Like we should come up with our own challenge. But then like these hashtags also help with discoverability. So like I have my own prompt right there, like that I just like I also just prompt engineered the prompt, so it makes sure that like the chapters are high signal YouTube chapters. It makes sure that like it properly spaces them. Yo, I'll just give you this prompt. I'll send you over this prompt. Yo, Alpha, why we got two alphas now? It's crazy. I'm gonna send you this prompt. Yo, Alpha, at some point, like since you've been playing it with Nano Banano, we really need to figure out like how we're gonna auto generate thumbnails. That's gonna be sick. I know you already do it, but like like just keep improving the quality too. Let's see. Yeah, Nano Banano is sick. I'm gonna send you my prompt. And then like OpenAI is just dropping their latest one, so we'll get to test that out. So this is my prompt usually. You could probably set up ChatGPT to like prompt it. Yeah, it's pretty sick. But yeah, you can figure out Alpha. Just figure out how you want to like break down the videos. But like, yeah, I think because when I was watching the videos, it's just hard for like I want to see how like how they flop it or something real quick. So usually I skip to it, but it's really up to you though. Also with the chapters and stuff, I think it gets indexed, and then like if people are searching for certain specific stuff, it adds like it adds like better. Yeah. Like when I look at when people watch my videos, they're watching it like it spikes a lot when like people are like actually coding or when people are like trying out solutions and stuff like that, or when I'm introducing the problem. Yeah, I sent you the prompt. Yeah. Once your interview series starts popping off, I'll come out of nowhere and try it and see if I flop it. Maybe like sometime in the next week or two. I need to prepare, cause you be asking some hard stuff. Yeah. Tho- those ones are the ones that pop off. But I literally can't make videos like that no more cause I'm not a senior SWE no more. But I promise you, as soon as I get back to senior SWE, I'm making vids like that again. Or I'll name the video Intermediate SWE does. Some people were telling me like, "Yo, just put senior SWE." I'm like, "Nah, it's weird, man. I'll feel like a fake." Yo, I figured out Advent of Code Part 2. It's like a I was here, you were at Google? No, I was never at Google. Alpha 2177, like you can find my LinkedIn by clicking through my profile. You find my LinkedIn. Did you want to take that job, Alpha? Like how's like the pay and all that stuff? Like you already have a good job. Yo, busy. You're just taking it for fun, huh? Wait, let me grab something real quick. Google SWE solving questions. Nah. Maybe I was putting like a Google SWE through some questions, but like I've been putting a lot of Google SWEs through questions. Or are you talking about like who you think I had a job there, Alpha? 2177? Thanks, bro. I mean, Google stock is going up. Maybe I wish I had joined that because that thing is going crazy right now. Busy. Where are you interviewing again? Yeah, the stock is doing good right now. It's crazy. Yeah. So this is linear programming. Yo, Alpha, I'll tell you this question, and it's pretty interesting. So for part day, which one is this? So for day 10, part 2, this one is a lot more complicated. I'll first read out the statement. So part 2. All of the machines are starting to come online. Now it's time to worry about the joltage requirements. And we don't really have to care about part 1 because part 2 is completely independent of part 1. So essentially, each machine needs to be configured to exactly the specific joltage levels to function properly. Below the buttons on each machine is a big lever that you can use to switch the buttons from configuring the indicator lights to increasing the joltage level. The machines each have a set of numeric counters tracking its joltage levels, one counter per joltage requirement. These counters are initially set to 0. So joltage requirements like 3, 5, 4, 7 means that the machine has 4 counters which are initially 0, and that the goal is to get all of them. The goal is to simultaneously configure the first counter to be 3, second counter to be 5, third counter to be 4, and the fourth to be 7. So initially we're given 4 counters that start at 0. And then we're going to be given a goal, for example, for each machine. So this machine, this other machine here, the goal is to get all of the counters to these numbers, 3, 5, 4, and 7. Right. Additionally, we're given a bunch of buttons. Each of these buttons, if you click one of the buttons, it affects different counters. So if you click button 1, it affects counter at index 3. If you click button 2, it affects the counter at index 1 and 3. If you click button 3, it affects the counter at index 2. Right, so these are all the different buttons. Our goal is to determine the fewest total presses required so that we can get to the joltage. So we need to figure out like how many times do we click, or what are like the minimum number of times that we can click the buttons in order to get to the correct joltage. That makes sense, chat? So we need to determine the fewest total presses required to configure each machine's joltage level counters to match the specific joltage requirements. This is the goal. Yeah, that's the goal. The answer is not DP. It's actually like a linear programming question. What do you mean? So for example, it's showing the different ways that you can click the buttons in order to get to this result. So for example, one way to do this, if you click here, one way to do this is by clicking 3 once. So if you click 3 once, you get this becomes 1, and then you click 1 3 1 3 times, so you get 1 1 2 3. Then you click 2 3 3 times. This button 2 3 3 times, so you get 1 2 3 1 2 3. Then you click 0 2 once, so this gives you 1 2. Then you click 0 1 once. You get or twice. I kind of messed it up, but like you do something like this. Isn't this just K job? So that's one way, and like you just need to make it match. I like messed up the number here, but you get the gist of like how you do it. What's the biggest each number can be? But like, what's the biggest each number can be? In what sense? Like probably, oh, like, okay. Are you talking about on this side? Like the joltage requirements? I tried that, honestly. I tried like a brute force, and it can get decently big, like 156, but there could be like a lot of different buttons. There could be like a lot of different buttons that you click to get there. Yeah, the input could be pretty large. So I just been like literally looking this up all day to figure out. So pretty much what you need to do is you need to it's like a linear programming question. So the way that you list it out is you want to get like a x equals like our goal. So suppose our goal is 3, 5, 4, 7, right? This is our goal. Let me move this down. It's like an integer linear program question. So if our goal is like this, right? And then we have all of these buttons. Yo, Javi, what's up? Wait, let me resume. So someone's asking why this is a linear programming question. Well, okay, this is actually how you solve this question. I had to do some research to figure this out. But we just need to figure out what ways we can hit the buttons in order to get the counters to this goal. So we pretty much mods in the building. But essentially what we need to do is we need to take all of the buttons, and it's like a linear algebra equation. But essentially we have a goal here, and our goal is to get 3, 5, 4, 7, right? And then we need to figure out x is pretty much how much we're gonna press each button. So if there's 6 buttons, it's gonna be a matrix like this. So how many buttons we have here? We have button 1, 2, 3, 4, 5, 6. So we have 6 buttons. So we're gonna have like x1, x2, x3, dot dot dot, x6. So it becomes a linear programming question, as in we need to find all these variables such that like if we multiply it, and then we build out the matrix like this. where we have every single button, like B0, B1. These are the different buttons. I'll explain it in a second. But essentially, for this one, for button 0 all the way to like button 6, if we click button 0, it really only affects it really only affects like button 3. So how it's gonna look is like if this is button 0 or counter 3, these are the different buttons, and this account we have 4 counters. So it comes like this. Counter 0, counter 1, counter 2, counter 3. But essentially we have 0, 0, 0, 1. Then the second button we have 0, 1, 0, 1. And then for 2 we have 0, 0, 1, 0. For 2, 3 we have 0, 0, 1, 1. For 0, 2 we have 1, 0, 1, 0. Then for 0, 1 we have 1, 1, 0. We have that. So these are our buttons, and why it's defined like it's a linear programming question, but essentially you just need to figure out the variables in X such that like if you matrix multiply these variables with the matrix of buttons, you get this result. Right? So there's multiple ways that you can configure these variables, these X's, in order to get this result. We just need to find like the minimum if you sum up all the X's. And then that you could pretty much brute force. But there's like multiple ways to solve that. That makes sense? So the reason why we have to I was just like chat GPTing this and trying to figure it out. But after when I was chat GPTing it made a bunch of sense. Like we have to define it as a matrix because clicking on the different buttons, like if you click this button once, it like affects. How close are you to 200K? You see it on the top left. Because if you click button, yeah, makes sense. You haven't done make stuff in a while. So if you click, so X1 means how many times are we gonna click button 1? If we click button 1, it's gonna do this to the system. So pretty much the solution is like you can just like define these variables, these matrices, and then just pass it into like a linear programming function solver that will minimize it, right? Because we essentially need to minimize this. But then like some other dude who hopped in the chat the other day, he did like a row echelon form RREF, reduced row echelon form, to figure out the free variables. And then essentially he just backtracked on the free variables. So I mean it's hard to just literally explain everything, but like if you work it out, you'll understand the solution. You just have to prompt GPT enough to understand it. So I was trying to figure this out for like at least an hour. But it made sense by the end of it. You just need to like really dig back into your linear algebra days. Yeah. So like somebody showed me like the easier that there's a SciPy function. Where is it? Like if you don't want to perform RREF to find the free variables and then like do a backtracking on the free variables, you could just use like where is this? Somebody sent me the code. Like for a very, like how did you, like he sent me this linear prog function. See, initially for day 10, day 2, I tried doing like the brute force solution, like, and then I explored like how to memoize it, and it wasn't solving it. But somebody told me that there's literally a function like this on SciPy. So let's see. So essentially all we need to do is programmatically figure out all these variables, and then we just plug it into this function. So it looks something like this. E4. So let's see. A equals B equals. And I asked GPT to break down this code as well. Where is it? So C is the objective function. So C is the objective function. Essentially, when we add 1, 1, 1, we're saying we want to minimize the total presses. This is means we want to minimize target. This is like the target vector we want to get to. So we want to get the counters to 3, 5, 4, 7, and then we need to just build this. We need to build this matrix like I mentioned here. Just build the matrix. And then we have to set the bounds here. What does the bounds actually do? What does the bounds do? Each button count must be greater than 0. Oh, we're just saying that the count must be greater than 0. And then this one, integrality. Gotta do some running back later, but this one essentially just means all variables must be integers. So effectively find the fewest total presses that reach the target vector. So all we really need to do is build out this, and then these are going to be set, and then we just call the linear programming function. So we just do that on every single line, and we should be good. And then under the hood, there's multiple ways to implement this, like this minimization, like the RREF, reduce row echelon form with backtracking is one of them, but I don't want to implement that right on the spot right now. Like, because also to do the reduce row echelon form calculation, they just use a library anyways. So and GPT said it's going to be pretty annoying to perform that yourself. So if I'm going to use a library anyways, then there's no point in doing the backtracking. I'll just use the SciPy library to just minimize the equation for me. All right, let's try this out. Wait, how do I start? Do I have a video on DP? Yeah, I have a video on DP. I talk about DP a lot. Why? Does DP confuse you? You just gotta practice with it a bit, honestly. Test. So I'm just gonna, so for the solution, I'm implementing the solution now. I'm gonna just import this. Yeah, it's really just practice, honestly. It's like my weaker one too, but I like when I practice it, I'm able to do them. But when I stop practicing it, those are the ones that I would forget. It's not like, yeah, some of them get complicated. Pip install SciPy. If you look up James Peralta DP dynamic programming, you're gonna find it. For line and input string. Yo, busy first, like understand the call stack. Look up James Peralta call stack and make sure you understand the call stack. That's gonna really help you when it comes to DP. That's like my main advice there. Like understand the call stack. I'll send you a video. Like if you can't visualize the call stack, it's gonna be hard for you to do a lot of things. Hey everyone. So today I'm Oh wow, this video is doing good right now. What the heck? Yeah, watch this. Understand the call stack. Understand recursion call stack. Because if you could visualize the call stack, then you could visualize like how you're gonna cache and memoize it. Yo, you got this, man. I'll be grinding with you. Parts. Voltage 1, 2, 3. You just missed everything after day 8. It's all good. It only goes to day 12, so you have a lot to go. I'll find it. I'll find it. I'm not sure if I do now that that you're asking, so I'll look for it if I do. Def. I'm gonna hold this. Target. 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 Length of target. Length of target. Length of target. So now we just need to build this. How do we build this? This is the buttons. We gotta kind of like create the buttons and transpose it. Is there function to transpose an array in SciPy? So we essentially want to just have all the buttons, and then we just need to transpose it. Oh, I want us to use. Once you hit 300 LeetCode questions, you're supposed to pass most likely FANG technical interviews like easily. Not really. I would say like it really depends on how hard you're pushing yourself. If you do 300 easies, that's a different story. Rows. This is how many rows we're gonna have. Then we're gonna pass in the button. Buttons. Oh, it's already 11 or 10. But we'll finish this up quick for call. So what we're gonna do is we're gonna get the bounds, then we're gonna loop for enumerate column for row in range row in button. We'll do equals. We'll take the row, we'll take the column, equals 1. Something like that. Then we'll run calculate min. We'll pass in the joltage. This is the result. And then we'll pass in the buttons. Oh. What is it complaining about? Okay. Okay, that's good. Oh, wait. The length of the buttons. Length of the buttons. What happened? How do you grab the result? Do this. Okay, it gives you 10, 12, 11. All right. Now we just need to run this on the actual, or we'll do result plus equal something like that. Print result. Actually run this on the actual now. Dude, that's so much faster. Oh no. What? What did I do wrong? Because we're trying to get the minimum, right? Linear prog. Wait, what am I doing wrong? It worked for the test. The goal is to crank out leak code company assessments. You got this, man. What? Make sure you're using full input data. Just Am I defining it right? So the rows is the length of the target. Let's see if I did this right. Balance target. Objective function, we want to minimize. Yeah, we want to minimize the value. I don't know the API for this. How do you use linprog? Oh, it's result.x. These are the optimal value or success. What's not fun? Please. What? Oh, you're right. Where's my bounds? Oh, we have to count these for element in. Does it change anything? Bro, it's not changing anything. Okay, I have to just view this. I don't know how to write this thing. What? Man, how did it work for the actual? Let's cook. I have to wait 5 minutes. I can't even solve. I'm gonna go. Let's get to day 10 before it's too late. I have to look into this. All right. I thought that we were able to get day 10, but we're going to move on to day 12. We're going to finish up day 12 when I click on this. Give me let me grab some water. All right. Final day. Final day of Advent of Code. We got pretty much every single day except for day 10 part 2. So it's time for the final day. Let's see how we perform. Let's get straight into it. Christmas tree farm. You're almost out of time, but there can't be much left to decorate. Although there are no stairs, elevators, escalators, tunnels, chutes, teleporters, fire poles, or conduits here that would take you deeper into the North Pole base, there is a ventilation duct you jumped in. After bumping around for a few minutes, you emerge into a large, well-lit cavern full of Christmas trees. There are a few elves here frantically decorating before the deadline. They think they'll be able to finish most of the work, but the one thing they're worried about is the presents. For all the young elves that live here at the North Pole, it's an ancient tradition to put the presents under the trees, but the elves are worried they won't fit. The presents come in a few standard but very weird shapes. The shapes and the regions into which they need to fit are all measured in standard units to be aesthetically pleasing. The presents need to be placed into the regions in a way that follows a standardized two-dimensional unit grid. You also can't stack presents. As always, the elves have a summary of the situation, your puzzle input. First, it contains a list of the present shapes. Second, it contains the size of the region of the number of presents of each shape that need to fit into that region. Okay? Okay, I see. So the first section lists that the The first section lists the standard presence shape. For convenience, each shape starts with its index and a colon. Then the shape is displayed visually. Okay, so this is the shape of 0. This is the shape of 1. This is the shape of 2. Oh, we're probably going to have to, like, make them fit under the tree in, like, a weird way. Allison, what's up? The first section lists the standard presence. The first section lists the standard presence shapes. Each shape starts with an index and a colon, then the shape is displayed visually, where hashtag is part of the shape and dot is not. The second lists the regions under the trees. Each line starts with the width and length of the region. So it's 4 by 4. 12 by 5 means it's 12 units wide and 5 units long. The rest of the line describes the presence that need to fit into that region by listing the quantity of each shape of present. 101032 means that you need to fit one present with shape index 0. No presents with index 1. One present with index 2. No presents with index 3. 3 presents with index 4. Okay. Yeah, this is like arithmetic. Presents can be rotated, flipped as necessary to make them fit in the available space, but they have to always be placed perfectly on the grid. Shapes can't overlap. That is the hashtag part from two different presents can't go in the same place on the grid, but they can fit together. That is okay, it's like Tetris. The elves need to know how many of the regions can fit the presents listed. In the above example, there are 6 unique present shapes and 3 regions. The first region is ... Okay. In it, we need to determine whether you can fit 2 presents that have shape index 4. Yeah. Yeah, you can fit 2 with index 4. What is this? 3 down. Yeah, you can do like this too. Yeah. After some experimentation, it turns out that you can fit both presents. Yeah. The second region is 12 by 5. It's 12 units wide and 5 units long. In that region, you need to try to fit one present with the shape 0, one present with shape index 2, 2 presents with shape index 4. Twelve, 5. Okay. Man, like, let's see. Let's look at the input. This is the input. This is a pretty interesting question. I feel like it's just like one way to brute force it is just using like a backtracking algorithm and literally brute force. So in a 4x4 grid, you have 1, 2, 3, 0, 1, 2, 3. Then we need to fit 0, 1, 2, 3, 4. This twice. So one way to do it is like have this. How big is the actual data? Yeah, we could see if we could brute force it. Ooh. 50. Oh no, yeah, you can't really. I don't know if you can, because we have to put 51 of these. Does it have to fit perfectly on the floor? Yeah, I don't know if you could actually brute force it. Let's see the rules for how it fits the region. The L's need to know how many of these regions can fit the presence listed. In the example, there's 6 unique and 3 regions. Okay, we're saying. Okay, the second list the regions under the tree. Each starts with, yeah. The rest describes the presence that needs to fit into it. Okay. 3 represents presents can be rotated and flipped as necessary to make them fit in the video, but they have to always be placed perfectly on the grid. Okay. Shapes can't overlap. That is, yeah, but they can fit together. That is, the dot part in a present shape diagram does not block another present from occupying that space on the grid. The L's need to know how many of the regions can fit the presents listed. In the above example, there are 6 unique presents and 3 regions. Okay, let's think about this a bit. I think solution 1 is just brute force it. Like literally for every single shape, find the possible. Like we know that we need to place. So for example, shape index 4. We need to place 2 of these. So we could just, one way to brute force is we're gonna like try for every cell and every try for every cell and every orientation. For every shape, try for every cell and every orientation. It's like this. So we'll just try to put like 1, and then now we place it, we can like mark the cell. But we only have 5 cells, or we only have 5 of these. 5. Try for every sound, every orientation. So we know we need to place 2 for sure, because we just need to fit 1 additional. Yeah, like one way is try for every shape, try every sound, every orientation. It's like, and we backtrack. True if we get to a result. So suppose we have like, oh, the input gets large because we have 46 by 43. So we have 36 places to put this, times 32 to place this. Let me do some math. Like worst case times. Let's do a calculator. Oh, wait. Billions? No, I don't work on ads. Why? What is that? Billions? 0, 100,000, 100 million, 100 billion. Yo, that's gonna take forever. Yeah, I guess we can just like look at the shapes. I guess it has to hit the floor though, does it? Or can they like be floating? No, shape 4 can be fitted with shape 3. Look if you put 3 there. Shape 4 could be fitted with 5. Yeah, you're right. 2, 4. because then it'll use up less space. Because if you have like 4s and if you have multiple 4s, it'll take up space. Yeah, you're right. That's a good insight. That's a good insight. So 4 could only be fit with 4 optimally. Because if you put anything else there, what happens when you fit 4 and 4? It takes up 2 space. Okay, but like, I mean, what if I fit this one in, like, if I do... rotate this. I guess you can figure out which ones go optimally. Like, you could just like figure out how you can combine all of these. Maybe if you could, maybe all of them, like the way to optimize is you combined it with itself. Like maybe that's like one insight that we can make, like the best way to optimize it is if you combined it with itself. But then this uses up too many corners. Like here. Yeah, but can we use that insight? Yo, Zero, what up? It's crazy. Because I think, yeah, maybe if we know like how to pair them up optimally, we can just figure out like how many cells there are, and then we could figure out like how many cells get reduced every time we like join them up. And then we just need to like backtrack on that, or how we fit them together. Or we just need to like do a algorithm to like match these together. Maybe we could be like 0 and make it fit in with 3. Like we can make them... Let's work on a small case. Like for this initial case, we have 4x4. And we know we need to fit 2 and 2 twice. Let's go back here. Let's delete this. And we know we need to, suppose this is the one we're looking for. So we need to fit 2 and 2 twice. What are the different ways that we can fit like the 4x4? We can use 4x4 like this. Or let's just like look at the different options. Like we have 4x4. What are the different ways? We can make them fit like this. This is variation 1. And that literally takes up 1, 2, 3, 4, 5. This literally takes up 3 by 1, 2, 3 by 6. 18. Like we just want to minimize. So it's like if this is like apart, or we could join them. I think we're getting onto something here. Dude, what the hell? We can join them like this. Like what's the total geometry here? This just takes up 3, 4. Realistically, we can't fit nothing there no more. We can fit this other. We can fit something else right here though. What are like the other options? We can have them sideways like this. This 3x6 also. We could also just stack them. Takes up 3x6 as well. So basically, you can know how much space you need at least. You need at least 3x6. So if you have like 2, what if you add a 4th? What if you add a 3rd? If you add a 3rd, you could only get this. Like if you stack it here or stack it in this corner, it's gonna make things worse. So I think Like you need to compact them, and then like the rotation doesn't even matter, because you can just compact them like this. Like you just need to figure out how to pack them as much as possible. Yeah. Like, what's the largest square you can get? I think all of them are 6x6. 1, 2. All of them are 6x6. That's one thing to note. All of them are 6x6. So I think we really need to only care in 6x6 slots. Yeah, you're right. That's a good idea. Oh, sorry, 3x3. 3x3 slots, because these are only 3. Or I mean 6x6, because I mean like we're gonna combine them, right? Like this one is like. Like it doesn't really make sense to fit any of them like right there. It makes more sense to like stack them together. Like would it make sense to like they all just partner up with the one that minimizes them, then we all just squish them together? We can get the difference between sum of all numbers and 6. Sorry, what do you mean by that? Oh, well. Oh, there's like some. Yeah. Yo, Paul, we need some help. That kind of makes sense. Yo, Paul, I'll show you the problem. Essentially, we're gonna be given like the problem is pretty simple. This is like the input statement. We're gonna be given a bunch of shapes. Let's see. Me and Igo have been making some good progress on this, but like essentially we're gonna be given a bunch of shapes, and then we need to return like true or false for every single like grid that could actually fit all of these shapes. So this one, so each element here is telling you like how many of these shapes do we need to fit. So for this one, we need to try to fit 2 of 4, right? So the way to, in a 4x4 grid, this, in a 12x5 grid, we need to fit 1 of shape 0, 1 of shape 2, 1 of shape 4, and, or sorry, 2 of shape 4 and 2 of shape 5. So we need to try to fit that in a 12x5 grid, and we essentially just need to count up how many times, like for how many rows you could actually fit the shapes into that size of a matrix. Does that make sense? You can get the difference between sum of all numbers and 6. Yeah, base. I don't know what that is. Okay. What is that equation gonna do? Yeah, trauma knows. Yo, yeah, this is it. But they just give you like 5 specific shapes. Yo, XVZ or XVX, what's up, man? Yeah, it was nice to see you too. Yo, this question is hard. Yeah, it's definitely some. Yeah, it's like a combinatorial problem. That makes sense. What the hell? Yo, I go. So what were you thinking of, like? You can fit the different shape 0 to 7 numbers. Yeah, I don't know. What's domino? Oh, okay, I see. I think there's like... Ooh. Dude, ours is like 6. I've seen a question like this before. Okay. It's not looking good. Not looking good at all. And 6. Damn. This is definitely on my tax bracket right now. Are you talking about the actual shape? 1 and 3? Like 1 and 3 here? Okay, I see. I see what you're saying. So you're saying from this set? Okay. What's the best way? Okay, the best way to fit this is this. Your input looks different? Oh, so they just can't copy you, huh? Three by 5. Then what? This is difficult. If you move it up here, it takes more space. It's like a greedy. This one takes 12 space. But maybe you can figure out like what's the smallest way you can. Let's just work on small example. Like if they give you two, if they just give you any two shapes. Two shapes. What's the smallest grid? How would we be able to define that? Well, for each one, we just need to pre-calculate. Like, what's the smallest if I have two of these? If I have... Maybe it's like a top-down DP. Or like bottoms up. Because if I have a 0, right? I know that I could ask myself, if I have a O, what's the smallest size that I can fit with an O? Then I'll be able to answer that for sure. It's literally 3 by 3. If I add another O, like for all of these, if it's just by itself, the minimum is 3 by 3. You need 3 by 3 space left. But what if you start adding? What if you go like... What if you go 0 and 1? What if you add 0 and 1? Bro, this is hard. What if you add 0 and 1? What's the smallest now? Why would you let GPT parse the input? What do you mean by let it parse the input? So all by itself there, but what if it's like 0 tied? We could try 0 with like all of the different ones. Oh, you can use GPT all you want, honestly. I'm not going to use it for this time, but... Maybe you can just pre-compute. So what's the smallest that you can add 0? Like if I had a 0 and 1, what's the smallest I can make it fit? Like what's the smallest, like what area is the smallest area I can make it fit in? Probably just side by side like this. Yeah. So it's gonna be 3 by 6. Or 6 by 3. It doesn't really even matter. Like 0 and 1. Dude, why does my 0 look like that? Oh, okay, I stretched it. I think with 0... Yeah. Because if you try to, like, place it here, though... Bro, I don't even know. Paul, what are you thinking? Like, what is... What are some of the approaches? What, and then you just try to force it? You think? Damn. Okay, wait. Let me take a break quick. Yo, this is cooked. Let me write down. Let me write down some of the approaches I'm thinking. So brute force it. Backtrack on every shape. Try every cell and orientation. But like I multiplied this out and there's way too many options. Oh, I guess, do you need to do it on every cell? If you could reduce the amount on every cell. Less. Well, I guess, yeah, we could just try every cell in every orientation in every order. And then we try to see how many like cells that takes up. And then we try to see if like we can fit that into the matrix. Like how many different combinations? Then could we even simplify it by saying like certain ones fit with the other ones better, so we just use that? Because we just think of like packing them all in. What we can, like, I'm wondering if like, what if we could just think of packing them in just one line? And then like the rectangle doesn't really matter. We'll figure that out after. First we'll figure out like what's the most that we can fit them in like one line like this. And then we could try to get it into the shape after. Paul, does that make sense? Or I go? Like literally just try to pack them all here. And after make them fit. Like depending, we'll be like, okay. I guess they really go by threes. And then sometimes like this might be four. What to do? Man, this question is way too difficult. Yo, Alpha, it's so hard. This question is difficult. Man, yo, I'll explain it to you and you're gonna be like, you might I feel like I seen it in leak code, but let's see. He got pipped where? What company? Yo, Alpha, essentially what we do is like we have all these different shapes, similar to Tetris. All the shapes are 3 by 3. And then each shape has like a label. So this is shape 0, this is shape 1, this is shape 2, this is shape 3, this is shape 4, this is shape 5, right? So we just need to see that given a 4x4 grid, can we fit 2 of shape 0, 1, 0, 1, 2, 3, 4? Can we fit 2 of shape 4 in a 4x4 grid? I see. Yo, M, what company is your friend working for? So we just need to see like how many of these shapes can we fit under in a 12x5. Like if it's even possible to fit them in a 12x5. So this is like 1 of shape 0, 0 of shape 1, 1 of shape 2, 0 of shape 3, 2 of shape 4. I see. Damn, they got pipped at ByteDance. So these are all shape, right? All shapes. So this is like just telling us try to fit the like 2 of shape 4 in a 4x4 grid. So it's possible because you can like if you have 2 of shape 4, you could just make it fit like this. That's literally what they said. You got to get more try to fit one present. Yeah, it's so weird. So my initial, like one of my brute force is if you had unlimited time, you could literally just brute force it, backtrack it for every shape, try for every cell and every orientation. So you just like try to place it and you just backtrack all the way, and then until you could see if you're able to place every single shape that you need to do. Right, but that just leads to like millions of combination. Like just that's the brute force. Can you just place them? Yeah, for this one, Alpha, take a look at this one. For the third region, 12x5, you have to fit like all of these shapes in there, and then you can get this shape. And look at the way that you have to fit it here, though. It's so weird. Yeah, I can't figure. I literally can't. I guess the question is pretty much asking, given X blocks. It's like a packing problem. Dude, I'll do C plus. I'll learn C plus plus next year probably. Given blocks, can you make them fit in a grid? It's like a packing problem. Optimal packing. Pause. iGo is like making some good progress on it. Dude, there's like a... Paul, what are you thinking for this? You got any suggestions? Or are you lost as well? Why do the AI labs want Rust devs? What's your question? What do you mean precalc all rotations? Okay. This was my initial thought. Paul, are you pretty much saying this? How do you? So what's your logic for? Let's see your code. Send me your code. Send me your code. How did you try to place it? Yo, send it in the Discord. Listen. So it's just a brute force. Damn. This one's rough. This one is rough. Let me call this guy on Discord. Nah, he might be doing something. Shabash, what up? Hell nah. Why don't you just send it to me on? Like, break it down. My God. Shit. When you place a piece, how do you figure out how much space it took? Sort pieces by size. Try to fit out in the grid using backtracking. What the hell? Just cooked. What the? Let's just run this on your. Where do you read the input? Yeah, I got cooked. I can't. Let's go. Pause the goat. Pause the goat. I'm not claiming that though. I need to look that up. Part 2. The elves thank you profusely for the help and start rearranging the oddly shaped presents. As you look up, you notice that a lot more elves have arrived here at the Christmas tree farm. In fact, many of these new arrivals look familiar. They're the elves you helped while decorating the North Pole base. Right on schedule, each group seems to have brought a star to put atop one of the Christmas trees. Before any of them can find a ladder, a particularly large Christmas tree suddenly flashes brightly when a large star magically appears above it. As your eyes readjust, you think you notice a poorly man with a white beard. You go only 23 stars to go. What? Paul's a legend, man. I need to look up that. The elves thank you profusely for the help and start rearranging the oddly shaped presents. As you look up, you notice that a lot more elves. As you look up, you notice that a lot more elves have arrived here at the Christmas tree farm. In fact, many of these new arrivals look familiar. They're the elves you helped find a ladder. A particular large Christmas tree suddenly flashes brightly with a large star magically appearing above it. What is it asking? Oh, it's not even asking nothing. There's no part 2, really? Damn. Yo, chat. We did it together. With Paul's help, with everyone on the chat. That was depressing. Yo, wait. Walk me through this. Thanks, Shabash. Build the list of pieces to fit each piece. Variations times count. Sort pieces by SARS. Size by SARS largest first. Does this way work always? Oh, I need to finish. Oh, I need to finish all the. Okay. I tripped out. Okay. Bro, this is so annoying. Like, I had it. Yeah, I got cooked on day 12. Bad performance, terrible performance. Thanks, Paul, for getting me on that, though. Ramen, what's up? Were you able to solve it? Dude, it's hard. Let's see what I'm doing here. Microsoft is chill? Yeah, I'm living good, honestly. What? Dude. Run. How'd he kill C++? I got cooked. I straight up got cooked. Not a great performance at all. What am I doing wrong here? Man. It wants me to use pulp. How did the guy make it work? How did that other guy make it work? Pay to play, baby. Bro, this thing didn't even give me proper Python code. What the hell is it doing? It like totally like messed up my whole thing. Five minutes? How did that guy optimize it? Okay, we might actually have to do like, but I didn't. Man. Not a good performance. Not a good. Atlas is chill. It's nothing crazy. Man, can't believe I got cooked like that. Man, I'm disappointed. My competitive programming dreams have been crushed. Code breakdown. Yeah. Okay. So we have a shape library. List of W's. Oh, is this? Oh, this is just. Oh, it's actually just straight placing them in the actual grid. Okay, I thought it was doing something fancy. So you literally have all the different grids, right? And it tries to place it. Then it tries to place the other one. It just finds different places to. Dude, this code is just weird for. I see. Oh, okay, I see. Yeah, it's kind of like it's actually just like the initial solution that I was mentioning. Why do you have to pre-compute, Paul? No valid placement. Why do you have to fit all the pieces for iron? Astronomical. Each piece can be 100. Yeah, I thought it was gonna time out, but it didn't. Dude, cook. Cursor, clean up Paul's code. Man, I got cooked. I can't even read code right now. Alright, we'll be back on this soon. It's still going up. Flop day 12. Dude, I tried day 10. I can't solve it, man. I need to really spend some time doing some research. Like, I ran it through that same algorithm that guy said he was using. This linear prog. And it didn't work. Yeah. No, we're gonna get better next year. I performed better this year than I did last year for sure. So maybe by the time I'm 40, I'll be able to actually solve one of these things. All right. Next time we stream, we're gonna be looking. We're gonna try to get this day 10 again. I'm gonna keep looking into it. Like, this is crazy. Man, disappointed. I should have been doing math competitions when I was a kid. Should be way easier. Did this question? Yo, like, I'm trying his solution. It didn't work for me. I'm gonna message him. Where's this guy? Vibe code what? You trying to vibe? Nah. We'll figure it. I need to get some sleep and we're gonna figure this out. Yo, thanks for tuning in. We're gonna be better next year. Appreciate you. And Paul, good job, man. You're a beast. I'll be working hard. I'm gonna try to catch up. Thanks for tuning in. Peace.
This is not my main thing, really I'm a coder. Coffee stains and in my chains, I am such a loner. San Francisco bases got me slowly taking over. I can't wait to show you that I'm gonna take it over. Beat code, beast mode, lead 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 code, beast mode. This is not my main thing, really I'm a coder. Coffee stains and in my chains, I am such a loner. San Francisco bases got me slowly taking over. I can't wait to show you that I'm gonna take it over. Lead code, beast mode, lead code, beast mode, lead code, beast mode, lead code, beast mode, lead code, beast code, beast mode.